So good afternoon, everyone. Our lab is membrane separation, and you guys know who we are. Yeah. Oh, so determination of the hollow fiber membrane separation factor alpha for the oxygen nitrogen experiment. So pretty much these are what the fibers looks like, right? And we all know how separation by membrane takes place, right? As you pump the feed through the membrane, due to pressure difference and selectivity, the oxygen, which is the permeate, will diffuse to the low pressure side. So the pressure is the driving force, and the nitrogen will be our reject for this experiment.
The main goals of this project are to generate oxygen concentration versus both the reject and permeate recovery percentages. For this, there's two conditions that we need to achieve. One that's 97% nitrogen or greater for potato storage, and another that's 32% oxygen or greater for just better efficiency for fields. From this, we want to generate data and determine operating conditions to be able to achieve both of these conditions on a plane scale system.
So, when we're considering the lab as a whole, there's three main determinations that need to be drawn for the eventual scale up of a pilot scale process, and namely for the membrane separation. So the first one being determination of membrane type, second determination of membrane flow model, and the third is determination of the set and controllable parameters that you would control in the lab. So that would be then what you would be able to adjust with the knobs and things. So going off of the first point of what kind of a membrane that we want to use, in the pilot scale model downstairs, the membrane is actually a dense membrane fiber membrane separator, and the membrane, as you can see here by this little diagram, there's three steps to this type of membrane separation. It's the initial adsorption of the molecules onto the interior part of the membrane. Those particles then diffuse through the dense membrane substrate and then desorb on the other side of the membrane into the permeate. And as you can see, this is kind of an example of the selectivity that is inside the dense membrane, as shown by the arrow thickness. Oxygen is much more favored by this specific membrane that's used in the lab. So that's how we're able to get a greater oxygen content in the permeate stream vice nitrogen, even though both still diffuse through. The next consideration for the lab is to choose the model that you wish to represent your experiment off of. We decided that the best one for this membrane lab was to be the countercurrent model, and that's because we came to that conclusion based off of the orientation of the inlets and outlet flows that were on the actual membrane itself on the pilot scale model downstairs. And yeah, so the data that you can gather from the pilot scale model are the three different flow rates, so the permeate, the retentate, and the inlet flow from the membrane, as well as the oxygen concentrations in the permeate and the retentate. And from those five variables that you can gather from the lab, you can apply them to this model to eventually calculate how you would expect the membrane to act.
Starting with the theory. So as what he taught us, we all have to start with just kind of basic mass balance. The yellow outlines are the values that we know, that we're able to record. And so starting with this, you kind of just know the inlet and outlet conditions. From that, we have to break apart the membrane into stages to be able to do analysis throughout. So you choose n number of stages and to get your fraction cut, FT. The greater the value of n, the more accurate your results are gonna be, because having a set FT forces the areas of each section you're observing to be different. So the greater the number of stages, the more accurate your results will be to be able to compare to. Once FT is found, you can start doing mass balances around however many stages you chose, finding FRJ and FPJ based off the previous or latter stages. With all of the mass balances done, you're able to do your first concentration calculation at YRN minus 1 using the YRJ equation found here.
And yeah, and so pretty much once you get those values, we're going to use this equation to find the YP and the YR around the J stage, and pretty much we're going to cascade it for the number of stage. So if we say like n is 100 stage, we're going to pretty much just like use these for those. But this is just representation of YRJ and YPJ for the J stage. And these are some of the parameters. So how we're going to find this is that we're going to use trial and error by just pretty much assuming values for alpha, and then to see if it converges. So if when we do it for the n number of stages, which is 100, we'll see if our permeate and our reject are the same as what we pretty much measure in the lab. And that will make us say, okay, cool, we actually have a selectivity for the membrane separation.
Any questions?